Hello everyone, I'm Tanvir Ahmed Khan, a final year PhD candidate from University of Michigan. Today I will present to you Whisper, a different kind of mechanism to predict branches. Before I describe this mechanism, let me start with the motivation behind our work. While preparing for this presentation, I searched for Micro 2022 on Google. This Google search took around 970 milliseconds. To serve that single search query, Google had to use 8 processor cores, and during those milliseconds, the efficiency for these cores were only 32%. Now consider serving billions of users all over the planet. Serving so many users means companies like Google and Facebook deploy millions of processor core in their data centers. Deploying so many processors over hundreds of data centers incur millions of dollars in operating cost. More importantly, these processors are responsible for the planet-scale carbon footprint and global warming. Even a single percentage of efficiency improvement for these data center applications have the same impact as reducing the carbon footprint of the whole country like Barbados. Therefore, if we can improve the processor efficiency for these applications, we can not only save millions of dollars but also meaningfully reduce the global carbon emissions. To do that, let us see why a single web service requires so much compute and where the CPU pipeline slots go. While performing Google search, 32% processor efficiency meant only 32% of all pipeline slots are spent in doing useful work, retiring instructions. All the other slots could not retire any instruction because of key bottlenecks in the processor microarchitecture. Almost 24% of all pipeline slots are lost due to instruction fetch issues. 15% of all pipeline slots are lost due to branch prediction issues. Finally, 21% of all pipeline slots are lost due to data cache issues. While my prior work have addressed issues regarding instruction fetch and data cache, in today's presentation, I will focus on branch predictor issues. First, I will investigate why don't the state-of-the-art branch prediction techniques overcome these mispredictions for data center applications. Based on our investigations insights, I will present Whisper, our profile guided technique to eliminate these mispredictions. Finally, I will show Whisper's evaluation. Let me start with the investigation. As described in the introduction, branch misprediction is a major problem for data center applications. We characterize the implications of this problem for 12 open source data center applications. For these applications, we measure percentage of CPU pipeline slots lost due to branch mispredictions, which we show in the y-axis, while lower is better. As we show, on average, these applications lose 11% of all CPU pipeline slots due to branch mispredictions. Now let us see why state-of-the-art techniques cannot avoid these mispredictions. State-of-the-art techniques use earlier branch directions or histories to predict future branch directions. In particular, they maintain a table of history and corresponding prediction for each branch inside microarchitecture. In this example, during branch A's last execution, previous two branches were not taken and taken. Here 0 denotes not taken and 1 specifies taken, and after that branch A was also taken. Hence, next time branch A predictor encounters branch A with a 2-bit history of 01, it would predict that branch A will be taken. This table is stored in the microarchitecture and hence has a limited capacity. For example, this table can only store histories for branch A, B and C. Now, if we program executes B with a new history, the table has to get rid of another entry, say branch C's entry, to store the next entry. The problem is, if C is executed again, the table has no idea whether this branch should be taken or not. For data center applications, this scenario happens a lot as they have a large number of unique branch instructions. As a result, data center applications suffer from a large number of branch mispredictions due to capacity issues. Now let us see how we solve this problem with Whisper. To solve this capacity problem, Whisper's key insight is to move prediction for some branches from hardware to software. One immediate benefit of this approach is that now we can store information for more branches in hardware, effectively increasing its capacity. Another significant benefit is that when we predict some branches via software, we can efficiently encode this large history table of a single branch using a single formula. Let's see how Whisper accomplishes that. Instead of memorizing histories as table for each branch, Whisper finds and stores a formula that takes these histories as input and produces the prediction as output. As both input and output of this formula are bits, this is a Boolean formula. From all possible Boolean formulas, Whisper picks the best formula in a profile-guided manner. In particular, based on application's profile, Whisper measures how accurately each of these formulas can predict the branch. Consequently, Whisper selects the formula with the highest accuracy based on the profile. Similarly, Whisper can also predict different branches using different formulas. In particular, we observed that with only a small fraction of all Boolean formulas that can be implemented with a simple combinational circuit, Whisper can predict a large fraction of all branches. Let's put all of this together with Whisper's uses model. First, in production, Whisper collects the data center application's execution profile using efficient hardware support such as Intel processors and last branch record. This profile includes two key information. First, branch direction for each branch and prediction accuracy for the underlying hardware branch predictor. Then offline, Whisper for each branch, Whisper determines whether a Boolean formula can predict this branch more accurately than the profile processor's predictor. Only for such branches with more accurate formula-based prediction, Whisper injects the formula and generates an updated binary. This updated binary is then deployed in production. In production, for branches without formulas, Whisper uses the hardware branch predictor, and for branches with formulas, Whisper uses the formula to predict the branch. Next, I will briefly describe Whisper's evaluation. To validate Whisper's effectiveness, we measure how much performance speedup Whisper provides over the 64 kilobyte Tej SCL baseline. This baseline predictor combines the benefit of both state-of-the-art prediction techniques, Tej and perceptron. We show this speedup in the y-axis, so higher is better. Across 12 data center applications, Whisper achieves an average speedup of 3%. In comparison, Tej SC with unlimited storage, which is almost a theoretical upper bound, achieves an average speedup of 6%. In other words, Whisper provides almost half of unlimited predictors benefits by reducing 17% of all mispredictions. If we can improve the performance efficiency of all data center applications by this same margin, we can have the same impact as reducing the carbon footprint of the whole country of Jamaica. In conclusion, in this work, we show that data center applications suffer due to frequent branch mispredictions as state-of-the-art techniques fall short due to capacity issues. To address this capacity problem, we propose Whisper that moves branch prediction from hardware to software for some branches. In particular, using a profile-guided mechanism, Whisper efficiently encodes correlations in a branch history using lightweight Boolean formulas. We evaluate Whisper for 12 widely used data center applications and show that Whisper achieves an average speedup of 3% by reducing 17% of all mispredictions. Thanks for watching my presentation. Please check out our paper by scanning the QR code above. Also, as our session chair mentioned, I am currently looking for tenure track faculty positions. Therefore, if you are hiring, please reach out to me via email.